In 2006, a team of astronomers led by Douglas Clow published a paper that has been cited for nearly 2 decades as the observation that settled one of the largest questions in physics. They were studying a system called the Bullet Cluster, two galaxy clusters that had recently collided and passed through each other about 3.7 billion light years away in the constellation Carina. They mapped the ordinary matter, mostly hot gas, using X-ray observations from the Chandra telescope. They mapped the total gravitational mass using gravitational lensing by measuring the distortions in galaxies behind the cluster. The result was simple and strange. The gas was in the middle, slowed by the collision. The gravitational mass was not. It was split into two clumps, sitting ahead of the gas, where the galaxies had passed through each other almost without interacting. Most of the mass in the system was somewhere the visible matter was not. The standard interpretation is that this is direct evidence for dark matter. The gas collided and slowed. The dark matter, which does not interact, passed straight through. The offset is exactly what you would expect if most of the mass is invisible and collisionless. That interpretation is not wrong, but it is incomplete in ways that matter. And the incompleteness is a good example of how the dark matter question is usually presented. I'm not going to argue that dark matter does not exist. I don't know that, and neither does anyone else. What I'm going to argue is narrower and more uncomfortable. The case for dark matter is weaker than it is usually presented. The case for the main alternative is stronger than it is usually presented. And the reason one dominates the field is not only evidence. This essay has 4 parts. What the problem is, what dark matter explains, where it struggles, and the alternative. The problem is older than most people think. In 1933, Fritz Zwicky studied the Coma cluster and found that the galaxies were moving far too fast to be held together by the visible matter alone. The cluster needed vastly more mass than it appeared to contain. In the 1970s, Vera Rubin and Kent Ford found the same problem in a different form. Stars in spiral galaxies orbit too fast, not just near the center, but far out in the disk. The rotation curves are flat. If gravity behaves the way Newton described, galaxies should fly apart. Something is missing. The modern answer is dark matter. Add a halo of invisible mass around each galaxy and cluster, and the equations work again. Rotation curves flatten. Lensing matches observations. Simulations produce the filamentary structure of the universe. At cosmological scales, the largest scales we can observe, this works extremely well. The cosmic microwave background, the large-scale distribution of galaxies, the growth of structure over time, all of these are described with remarkable precision by a model that includes dark matter. This is the strongest point in its favor, and it matters. Any alternative has to match it. But there is a gap between scales. Dark matter is strongest where structures are largest. Clusters, cosmology, the early universe. It is weakest where structures are smallest, individual galaxies. And that is where the problems begin. First, we have never detected it directly. For 40 years, increasingly sensitive experiments have searched for dark matter particles interacting with ordinary matter. Deep underground detectors, cryogenic targets, massive collaborations. Nothing. This does not rule dark matter out. But it has changed its character. What began as a relatively specific hypothesis, particles with certain masses and interaction strengths, has become a moving target. As experiments rule out one region of parameter space, the theory shifts to another. That flexibility keeps it alive. It also makes it harder to decisively test. Second, the satellites. Simulations of cold dark matter predict that galaxies like the Milky Way should be surrounded by hundreds or thousands of smaller satellite galaxies. We see about 50. Some may be too faint to detect. That is plausible. but it is also difficult to verify. Third, the ones we don't see should be the easiest to see. The simulations predict not just many satellites, but some that are quite massive, massive enough that they should contain stars. Those are missing too. Fourth, the centers of galaxies. Simulations predict that dark matter density should spike sharply toward the center, a cusp. Observations, especially in dwarf galaxies, show something flatter, a core. This is not a subtle mismatch. The shapes are different. Up to this point, these are problems of counting and structure. The fifth problem is different. It is a pattern. In 2016, McGaugh, Lely, and Schombert analyzed 153 galaxies. For each point in each galaxy, they compared two things: the gravitational acceleration you actually observe, the acceleration you would predict from the visible matter alone. If dark matter is an independent component, these two should not line up perfectly. The visible matter and the dark matter halo can vary separately. They do not. The relation is extraordinarily tight. Given the visible matter, you can predict the total gravitational behavior of the galaxy, including the part attributed to dark matter, with almost no scatter. It is as if the galaxy knows about a component we cannot see. There are ways to reproduce this in dark matter simulations, but they require careful tuning of how normal matter and dark matter interact during galaxy formation. And crucially, this pattern was not predicted in advance by dark matter. It was predicted by something else. There is a simple way to think about that alternative. Imagine gravity is not wrong everywhere, only in a very specific regime, not at large distances, not at small distances, at low accelerations. Mordechai Milgram proposed in 1983 that below a certain tiny acceleration scale, about 1.2 times 10 to the power of minus 10 meters per second squared, gravity stops behaving exactly like Newton's law and becomes slightly stronger. You can think of it like friction that changes when motion becomes extremely slow, or like a material that behaves differently under very small forces. Above that scale, everything looks normal. Below it, the rules shift. Apply that idea to galaxies, and several things fall out immediately. Rotation curves become flat. The Tully-Fisher relation emerges naturally. Low surface brightness galaxies deviate more strongly, exactly as observed. And decades later, the radial acceleration relation appears automatically from the theory. At the level of individual galaxies, this works extremely well, better in many cases than dark matter. This is not controversial among specialists. The disagreement is not about whether MOND fits galaxies, it is about what that means. But MOND has its own problems. The largest is scale. At cosmological scales, the cosmic microwave background large-scale structure, dark matter provides a clean quantitative fit. MOND does not, at least not in its original form. Relativistic extensions exist. Some are promising. None have yet matched the full success of the standard model across all cosmological data. Galaxy clusters are also a problem. Even with MOND, there is still missing mass. Not as much as in Newtonian gravity, but not zero. And that matters because it starts to look like the same move MOND was trying to avoid, adding unseen components to fix discrepancies. Which brings us back to the bullet cluster. The bullet cluster is a real challenge for MOND. The separation between the hot gas and the gravitational mass suggests something that behaves like collisionless matter. That is exactly what dark matter predicts. But it is not a perfect case. The collision appears to have occurred at an unusually high velocity, which is somewhat difficult, though not impossible, to reproduce in standard cosmological simulations. Other cluster collisions complicate the picture further. Some match the bullet cluster pattern. Others, like Abel 520, do not fit cleanly into either framework. The honest reading is this. The bullet cluster is strong evidence that something behaves like unseen, collisionless mass in at least some systems. It is not, by itself, a complete proof of dark matter. So where does that leave us? With an asymmetry that is easy to miss. At cosmological scales, dark matter is extremely successful and Mond struggles. At galactic scales, Mond is extremely successful and dark matter struggles. Neither framework cleanly spans both regimes. That is the situation. Not a solved problem, but a split one. The remaining question is why? Given that split, one side dominates. Part of the answer is evidence. Cosmology is a large part of physics, and dark matter fits it well. But part of the answer is structural. Adding a new particle is something physics has done many times successfully. Changing the law of gravity is something it has done once. One is an extension, the other is a rewrite. Fields also stabilize around their tools. Dark matter has experiments, detectors, simulations, and large collaborations built around it. Mond does not at the same scale. That difference matters over time. None of this tells us which theory is right. It tells us what kind of problem this is. A direct detection of dark matter would resolve it immediately. A galaxy that definitively violates Mond would resolve it in the other direction. A relativistic Mond theory that matches cosmology would change the balance. None of these have happened yet. So the honest answer right now is that we do not know. If you are not a physicist, that uncertainty is easy to misread. It does not mean the field is broken. It does not mean the consensus is meaningless. And it does not mean the question is settled. It means you are looking at science in the middle of a real problem, where multiple explanations coexist, each incomplete, where evidence points in different directions at different scales, where the final theory, when it arrives, will probably not look exactly like either of the current options. 95% of the universe is currently attributed to components that have not been directly detected. That is not a stable endpoint. Something will change. And when it does, it will not be because a single observation suddenly overturned everything. It will be because tensions like these were there all along, visible, arguable, and unresolved, until a better explanation made them make sense all at once. That is the case against dark matter. Not that it is wrong, but that it is not yet complete, and that the alternatives are not yet dead. The honest position is uncertainty. And that is exactly what you should expect from a problem we have not solved.